the clock is at 9:01, so my Swiss part asked me to, it's a standard joke, right? I'm to a good extent Italian, but being Swiss, I have somehow to keep a balance between timing and delay. So it's a great pleasure to have you here this morning at this GFAC invited lecture. I think it's an important moment of the conference, as every year, to recall the contribution and the legacy of Hal White to our profession. In contrast to most of you, I didn't have really the chance to meet Hal personally, but I had a big chance to meet him virtually by reading first his books, where I had the impression was the first time I could actually understand something really deep about econometrics, and then of course all the various papers. So today we have I think a fantastic session on a very hot and important topic, essentially the study of factor structures in panels. We're going to have as a speaker Patrick Gagliardini, and then two great discussions with Markus Perger and Alex Kionaski. So Patrick is a professor of econometrics at USI, the University Svizzera Italiana in Lugano since now many years. He has been previously assistant professor in St. Gallen. He's a fellow of the Econometric Society, and I guess most of you know at least some of his papers. He works in many areas, from semi-parametric option prices to non-parametric estimation of copulas. More recently, of course, panel factor models with mixed frequencies, and so on and so forth. Now, if you go through his webpage to make a kind of very brute force statistical analysis, well, the first thing you notice that is not updated. The last information is only until 2019, but of course I have some inside information, so that's good. The second thing you can make is to make a very simple study of what is the kind of way to predict his next publications. And I realized actually it's very simple to predict the next publication for econometrics, basically because every three years there is one. Okay. Now you may say that's already an achievement, but you should also know that Patrick is not only a very great researcher, he's also a strong helper to the community. Actually, he's now, 6 years ago, he was the dean of the faculty in Lugano, contributing to a lot of its organization. And more recently, since this was not challenging enough, he became pro-rector for research for the whole university. And despite that, you see, the pipeline of the work is not decreasing. So I'm really wondering how he does it. He must work during the night on the papers and during the day in the meetings. In any case, we are very happy to welcome here Patrick for the presentation. The floor is yours.
Thank you, Fabio, for the very kind introduction. Thanks a lot, and thank you to the organizers, of course, for having invited me to present this lecture. This is a great honor, of course, and really a pleasure to have this opportunity. So thanks a lot. My presentation is going to be based on a joint work with Alain-Philippe Fortin, who is sitting there, a PhD student from Geneva, and my colleague and friend Olivier Scaillet. This paper is about testing hypothesis on the numbers of latent factors in a short panel, which means that you have observations on many series, but just a few numbers of dates. So this is a practical and relevant questions when, for instance, analyzing the pervasive risks in a panel of individual stock returns. And we think that the small t feature of this analysis is useful because, for instance, it allows you to investigate general forms of time variations, for instance, in the numbers of factors or the factor structures, for instance, through the different market phases. And indeed, this is what we are going to do in our empirical illustrations. When the numbers of data time points is small, the identification of the numbers of factors is more difficult, actually. This is because we have some sort of error in variables in estimating our betas, of course, in a finite time span. Or if you want, there is a sort of incidental parameter problems. That is, we have a lot of beta loadings to be estimated in the panel, but just a few time observations. So this is why we need more structure in this small t setting for the identification of the numbers of factors. And in the paper, we are going to use mainly two possible assumptions. One is a sort of sphericality assumptions on the error, which I'm going to develop in much more detail. And another one on which probably I will have less time is about the use of instrumental variables also for this problem. So the main contributions of this paper is to develop new test statistics, which are based on the spacing between the eigenvalues of some small dimensional variance covariance matrices to test about the number of this unobservable factors. We are going to develop the distribution, the asymptotic distributional theories of this statistics. Of course, in the case of testing strong factors versus no factor, but also extending to some forms of more nuanced or intermediate trends in the factors, like semi-strong factors, weak factors, and this kind of things, which we know are quite important in this analysis. Instrumental for these developments is a new second-order perturbation expansions on the behavior of the small eigenvalues of a symmetric matrix, which is useful for what we do, but we think has some potential usefulness beyond the type of applications we are using here. And finally, we apply this methodology in a very preliminary empirical analysis. We do find evidence that the factor structure is indeed varying with the market phases, finding much less factors during the market downturns, more factors during market upturns, based on the p-values of this statistics. So maybe some words about the links of this work with the literature. Of course, this is contributing to the panel asymptotics with large n and small t. We know Carlo, who is in the room, of course, is there, as a very important work recently in this area, establishing asymptotic properties of PCAs in this setting, and also the selections on the numbers of factors in this setting. In this paper, we do testing about this number. There is a very extensive literature about selecting the numbers of factors when the panel is large in n and t in the 2 dimensions. Results are more scarce in terms of testing. Again, in the large n and large t setting, the first contribution is perhaps the work of Connor and Koracic in testing for the numbers of latent factors in this setting. We have the very important work of one of the 2 discussants, Alexei, with deploying essentially the characterizations of the largest eigenvalues of a Wishart distributed matrix in terms of Tracy-Widom load to construct this testing. And in fact, so the paper of Onansky of Alexei was also very useful to introduce random matrix theory, or popularizing a little bit random matrix theory among econometricians. That's a beautiful theory. It's also helpful in factor analysis. And our paper is also to some extent a little bit related and contributing in this area, because as you will see, the asymptotic distributions of these statistics are essentially involving the eigenvalue spacings in sort of random matrices of the Gaussian type, but in a small dimension, in finite dimension, because for us t is fixed. So as I said, the analysis with small t is a way to investigate general forms of time variations in the factor structure. Other streams of the literature does this with conditional models. Here I have some hints about that, some work, some of them also by Marcus, who is sitting here. Is going to be a discussion, a very rich area of recent research. This work is about alternative to this one, proposing following the different streams in which you work in finite periods. Okay, so this is the outline for the rest of the talk. So in the first part, I will devote some time in developing the theory for this test. So I will start by discussing the identification of the numbers of latent factors via these assumptions of sphericality in the error terms, and based on that, I will introduce the test statistics we are going to consider. Then I will spend some word on this second order expansions for the small eigenvalues in symmetric perturbed matrices, which is then going to be the key for obtaining the distributions, the large sample distributions of our test, both under the null and, let's say, local alternatives characterized by weak factors. And indeed, if time allows, I will also talk about a new test for weak factors, that is a test in which the null hypothesis is weak factor against the alternative of a strong or semi-strong factors, and possibly also touch a little bit on a alternative way to identify the numbers of factors when we don't have sphericality of the error terms, but we use instrumental variables. Then in a second part, I will show some Monte Carlo results to convince you, hopefully, that the method works. And then I will conclude with some results about an ongoing empirical analysis in which we test for the numbers of factors in short subperiods of the quiz panel. Okay, so here is our factor model. So a standard specification. The yi is a t-dimensional vector with the return or excess turns on the stocks. Capital F is a t by k matrix with the unobservable values of the factors, and the epsilon I is the t-dimensional vector of the error term, the idiosyncratic error terms. So the goal of our analysis is to test about this integer k, so about the numbers of factors in a setting in which we have a large numbers of stocks. So n is denoting the numbers of assets. So n is going to be large, but t is going to be fixed and possibly small. To start with, I'm considering situations with strong factors. So the Varkov of the betas is positive definite, and I will leave for later on the extensions. So if you want, this is a model in which with fixed t, we can consider this matrix F of the factor values as the parameter, the common parameter in this panel, and the beta i's are sort of incidental parameters, and we have many of them. So this is why the identification is more difficult than in a situation with large t. And in this first part, I'm going to assume this condition in assumption 1, which we call as sphericality of the error terms. It's basically assuming that average across the cross section, the variance covariance of the error term is a multiple of the identity. Okay, I stress that this is an assumption about the unconditional variance covariance of the error term, so which allows, for instance, at the level of the individual series forms of heteroscedasticity, but is excluding, for instance, strong factors in the error terms. Now, it is known since a while that this is a condition which is sufficient and necessary for the consistency of principal component analysis estimator with fixed t. And the reason is essentially when you develop the variance covariance or the second order matrix of the error term, you have basically the reduced rank structures from the factors plus the contribution of the error term, which is just this multiple of the identity. So the effect is just to move up or down uniformly all the eigenvalues of this matrix without changing the eigenvectors. So this is why in this setting, essentially the patterns or the profile, if you want, of the eigenvalues of this matrix is such that after a while, the eigenvalues become constant. So the profile is flat. Or in other words, this spacings or differences between two consecutive eigenvalues. So I will use the notations of this delta j's for the ranked eigenvalues of a matrix. this difference will be 0 after a while, and exactly starting from k plus 1. So these allows for the identification of the numbers of latent factors from the point on which this eigenvalue difference are going to be 0. So this suggests a way to construct possible test statistics in this setting. So first of all, you consider the sample versions of the second moments of the y, and then one first possibility for a test statistic is this one, in which you consider the difference between the k plus 1 eigenvalue and the last eigenvalue. So knowing that under the null, this difference is going to be 0, while if you have more factors, this difference will be larger than 0. Another possibility, which is inspired by the work of Alexei in large T, is to consider the maximal ratio between eigenvalue differences, which is this statistics S star there, with the idea that if the true number of factors is more than k, one of this ratio will be something like constant divided by a 0. So it will blow up and will detect the alternative to the number k. Okay. Notice that this statistic is basically a telescopic sum of all the eigenvalue differences between k plus 1 and the last one. So it's a way to aggregate these differences, different from this one. And for sure, there are other ways to aggregate the information which is contained in this differences here, possibly better than this. Okay, so essentially, then to develop the critical values for the statistics, we have to figure out the behavior of these eigenvalues here. So this is why we need, or we are using in the paper such a result, which is a sort of expansions for the behavior of the small eigenvalues of a symmetric matrix subject to a perturbation, the perturbation being the statistical errors that you have there. Okay. So let's say you have a matrix A, symmetric, reduced rank K. This is the eigenvalue, eigenvector decomposition. So D is the matrix of the non-zero eigenvalues. U is the matrix of the eigenvectors. And imagine that you perturb this matrix by adding some noise, this phi of K, a small one. Then you can write an expansion for the small eigenvalues of this matrix A at, and the small eigenvalues are the one starting from k plus 1, k plus 2, etc. So they can be written as the largest eigenvalues of this matrix here that involves a linear and quadratic term in the noise, psi h, and a reminder term. So a notable feature, and that's a second order expansion. As you see, the reminder term is third order as expected. Now, a notable feature of this expansion is that this term is uniform in the sense that you can show that this remainder is smaller or equal a universal constant times this one. Universal meaning the same constant for whatever matrix A you are expanding around. So this allows you to understand how this reminder term behaves depending on some features of the matrix A, possibly letting some of the eigenvalues of the matrix A, which are non-zero, to be very close to 0, and you control for this fact by means of this matrix here. And this is useful, for instance, when you have less definite setting than strong factors versus non-factor, like the weak factor ones. But okay, for us in this paper, that's a way to understand the behavior of the eigenvalues, because you can write this sample matrix of the variance covariance matrix of the return as a sum of these two components. One is a rank K plus a multiple of the identity, and then we have this perturbation term, the estimation noise, which is at the order, not surprising, 1 over the numbers of series plus a bunch of terms. Some of them will be killed in the asymptotic, so they are not very interesting. And this one is the term which is driving the behavior of this small eigenvalues. Now, under the assumptions of sphericality, essentially these terms are sort of mean zero averaging, or almost mean zero averaging. So we can have a sort of high level conditions that this quantity here in the estimation error is going to be a Gaussian variant, okay, because of a CLT. And then if you plug in this result in the previous expansion, you basically get the asymptotic distributions for these statistics, for the one based on the differences between the k+1 and the last eigenvalue, and the one based on the ratios. And the asymptotic distributions involves the eigenvalues of this matrix Z star, which is this pre and post multiplication of the Gaussian matrix Z by the matrix Q, Q being a matrix with T minus K columns, which are the orthogonal complement of the matrix F with the factor values. So basically the matrix Q is the way in which the factor paths, the values of the factors impact possibly on the distribution of the test statistics. Under the alternatives, this object diverges so that the test is consistent. So this basically means that to get the critical values for this statistics, you need to investigate the behaviors of these eigenvalues of this random matrix. So these are distributions which are in general known standards. So I will spend some time in discussing these distributions. So let's imagine to start with that the error terms are Gaussian, independent across time and stocks. Then it's quite easy to see that in the previous assumption, the matrix Z from the CLT has a very particular structure. So once you scaled by the square root of Q, Q being a sort of average squared variance of the error terms, the elements on the diagonal of Z are normal 0, 2, and the elements outside the diagonal are normal 0, 1, and they're all mutually independent. So this is a very well-known structure in random matrix theory, which goes under the name of a Gaussian orthogonal ensemble, which has been extensively studied in this literature. Now, but the rotational invariance of the Gaussian distribution, also the Z star with the pre and post multiplication, is again in the Gaussian orthogonal ensemble. So at the end of the day, what you get is that these statistics are basically, first of all, pivotal in the sense that they are not depending on the sample path, and they are involving the eigenvalues from these ensembles. Now, just to give a little bit of a features about what these things are. So that's the case with the two-dimensional matrix. This is very well known. So this in this literature, the difference of the eigenvalues are distributed according to this law, which has this name by the physicists first studying this distribution. Of course, you know that this has been very much studied, especially in domains in which these are related to energy levels in physical systems. This is nothing but twice the square root of a chi-square variable. Okay. This is what happens in the three-dimensional case. Here you have two eigenvalue spacing, the difference between the first two eigenvalues and the difference between the second and the third. You can give the joint distribution. So these are the level curves. You see some tendency in the tail to have realizations in which maybe the first difference is large and the second is small, or vice versa. This is probably because the trace of these matrices are Gaussian distributed, so you can't have overall a too large difference between the spacings of all the eigenvalues. And briefly, you can also obtain laws for the difference between the first and the last eigenvalue, or the distributions of the ratios of the two things, which are given in this respectively in the blue curve and in the red curve. So this basically means that if you are in a situation in which T minus K, so the difference between the numbers of time points and the numbers of factors you are testing is equal to 3, basically for the first statistic, you need just the critical level of the blue curve, and for the second statistic, you need the critical level of the red curve, and you can probably generalize to other levels. At the other extreme of this, so when t is very large, this is also an area in which very nice results are available, and this is our connection point with the work of Alexei. Very naively speaking, you may imagine that the pre-multiplication by the matrix Q leads to some forms of averaging across times of these errors, so that even if the errors are not Gaussian distributed, at the end of the day, the Z star matrix is sort of close to some Gaussian distribution in this Gaussian orthogonal ensemble. And in this setting, for a large dimensional matrix in this family, it is known that the largest eigenvalues are distributed according to a Tracy-Widom law. And that's the connection with the work in testing for the numbers of factors when t is large. This is just a sketchy link between the two. Of course, developing this is much more sophisticated, and this is the beautiful work that Alexei has done. Yeah, to make a step forward, what in the case in which the errors are not distributed Gaussian, or it's too nasty to get critical levels for this statistics, an alternative is to work out a procedure that works in a more general setting. Under some conditions, what you will have is that the matrix Z in the asymptotics will have a Gaussian distributions in the diagonal with a variance eta, which is this average variance of the squared errors, which in the non-Gaussian case is going to be different from 2 times the previous Q coefficient. So it's a bit of more general setting. And in this case, the distributions of the two statistics will involve also the patterns of the factor paths. Okay, and in the paper we discuss a procedure for a feasible statistics, which goes through estimating these unknown parameters, the Q and the eta, by means of the residuals. Without entering into the details, maybe some things that we have to be careful about is that when t is small, the residuals of the panels are in some sense not consistent estimators of the true residuals when t is finite. So you need some forms of bias corrections, if you want, in these errors. And then you get the critical values by simulating the Gaussian draws from this family. Okay. So far we have mostly addressed the setting with strong factors versus non-factor. Now I would like to spend some word on how do we extend this to more nuanced forms of factors. So we can do like this. So this is the second moment matrix, if you want, of your beta that you can rotate to have a diagonal if you want. And then you can parameterize these eigenvalues on the diagonal by allowing them to go to 0 at a certain rate, the rate being this exponent kappa here. So at the extreme, if kappa is equal to 0, that's a strong factor. If kappa is, let's say, very large, this is basically the eigenvalue is equal to 0, but you have a continuum between the two, something like values of kappa in between 0 and 1/2. It's what in the literature has been known as semi-strong factors. Then there is the threshold or value of 1/2 in which the size of the eigenvalue is at the same level of the estimation error, if you want. And beyond that, you have somehow a vanishing factor. Okay, so here is the goal. How can we extend some of the previous results if you want to differentiate these different forms of factors? Okay, the first result that we have in the paper is that the previous result can be extended to the case in which the testing is between strong or semi-strong factors versus vanishing factors. So you can consider a null hypothesis of this type in which up to some level k, you have factors which are either strong or semi-strong, and after k, they are just vanishing factors, and the previous two statistics are consistent for that, and they have the same asymptotic distributions in this setting. Then a second analysis that we perform in the paper is a sort of power analysis. So we can think of the weak factors as a sort of local alternative hypothesis to this setting. So having an additional factor, which is a weak factor, is somehow a local hypothesis. So let's imagine you have a local hypothesis like this one, in which you have, let's say, k factors which are strong, and then factors number k plus 1 is weak in the sense that it goes to 0 with the sample size like square root of n. So I should have mentioned that, of course, you see that this is a structure like with a Pitman drift in the data generating process of these things. So what happens in this situation? So under this local alternative in which the k plus 1 factor is weak, the asymptotic distributions of these two statistics are this one. In this case, the random matrix whose eigenvalues control the distribution is this Z1 star here, in which the original matrix has been shifted. So you may think of this as a shifted distribution, in which in the upper left element of the matrix, you have the sample size t times this coefficient c, which is basically measuring the strength of this factor here. So, and based on that, you can perform some analysis about the local power of this objects. So here, for instance, is a picture which applies when t minus k is equal to 3, and we have Gaussian errors. Now, with Gaussian errors, because of the symmetry in the Gaussian orthogonal ensemble, this local power does not depend on the patterns of the factor values realized in the sample, but it just depends on this coefficient here. Now, notice that if you divide this quantity by square root of n, so the ck plus 1 divided by square root of n, this is basically the standard deviation of the variance of the betas associated to the weak factor, so the variance contribution from the weak factor, and divided by this the square root of q, which is a sort of object related to the variance of the error term. So basically, this part is a sort of signal to noise for the contribution of the weak factor. Scale by t is a sort of concentration parameter in the ID literature, okay, which is what I display on this horizontal line. So, as expected, this power curves are upward increasing. Here, these are the two for the two statistics that we considered before. So we noticed that this statistics based on the difference between the k plus 1 and the last eigenvalues shows more local powers against the weak factors compared to the ratios one. Very quickly, so when the errors are non-Gaussian, the distribution is more sophisticated because the factor path will play a role. So this what you can illustrate in a case t equal to 2, k equal to 0. So you have a panel with two waves. You are testing for absence of factors in this panels. So in this case, the local powers, again, weak factors depends not only on these concentration parameters, but also on a measure of non-Gaussianity of the error terms, and also on some parameter which is related to the factor path. Remember that the Q matrix is the matrix which is orthogonal to the factor path. So that these are in some sense, the factor paths which are not in the sample. And so, in other words, this Q11 square, you can interpret as the square of the normalized factor value of the weak factor that you have in time 1 in your panels. So here you see that we see that the power with the non-Gaussian DGP is a bit smaller, and it depends on the value of this parameter Q related to the factor path. So I think that this is going to depend on the factor path. Okay, to conclude on this part, another result that we have in the paper is also a test for weak factors. So here, what we're going to do is that we have the weak factors under the null hypothesis. So the null hypothesis is the factor number k is a weak factor, and the alternative is that this factor is instead strong or semi-strong. So that's a way to see whether you find an evidence for the fact that the factor that you have in your model that you have detected is strong if you reject the weak one. So the way to do that is, again, to use an eigenvalue difference. We can get the asymptotic distributions on that. Unfortunately, the asymptotic distribution is unfeasible because it depends on some feature of this weak factors. But because there is an asymptotic distribution which has been established, we can use a subsampling procedure to get the critical values for this test. So probably in the interest of time, I'm going to skip this this part. So this is a part in which we try to go beyond the assumptions of spherical errors and show that another approach to identification of the factor values is through instrumental variables. So here, instrumental variables means a vector of assets characteristics Zi, which are, let's say, cross-sectionally uncorrelated with the error term, but cross-sectionally full rank correlated with the beta matrix. And in the paper, we show that if this holds, if you have such variables, again, you can construct a identifiable variance-covariance matrix for the data, which again has a pattern such that you can identify the numbers of latent factors, identifying when the eigenvalues of this matrix become zero. So similar to before, but I will skip this part. Okay, so let me move to showing some Monte Carlo results. So this is some preliminary experiments in the paper. So in a first DGP, we have simulated a model, let's say, with 3 factors. Very simple Gaussian errors to start with. Cross-sectional dimension is 1000. So we simulate path with this panels with the same realizations of the factors, and also many panels with different realizations of the factors in order to study also what is the effect of the factor paths on the behaviors of the statistics. So these are the size and the powers of the statistics for different values of t's. So in this experiment, the size is quite close to the nominal 1 or 5%. The power is quite good. Again, this statistics shows more powers than the other. The numbers that you see in parentheses are the standard deviations for these values across different realizations of the factor values. So because these are Gaussian errors, this is just a finite sample effect, because in the asymptotic distribution, it should disappear. So as you see, they get very small when the t is larger, and they will get very small also if we would repeat this experiment with larger n. But this shows that in a finite sample, it can have some effect. In design number 2, we allow for different forms in this third factor. So it's parameterized again in this way, and we consider different values for the exponent kappa to have a strong, vanishing, weak, etc. in this factors. So in this table, we report the rejection rates when you are testing for 2 factors with this DGP. The different columns refer to the different values of this kappa. So you may have a strong factor, semi-strong, weak, etc. 4 different values of this constant C in front of this. So essentially, on that part, basically you have to interpret these numbers as sizes for the statistics. Here we have a vanishing factor. So in this part, the size is rather close to the 5%. In this part, you see that when the values of the betas of the factors is larger, of course, you have some tendency to an oversize effect. According to the theory, when n increases, this is going to converge to 5%. So in any of this column, you will have, when n is large enough, convergence according to the theory, to the 5%. On that part of the table, this is power. So power is rather large, especially in this part. So of course, the closer you are to the strong factor and the bigger is the coefficient C, the bigger is going to be the power. And here again, you have low power when C is small, as expected, and all these numbers will converge to 100% when n is increased. In the middle column, there is essentially power towards weak factors. So this is related to the curves that we have seen before. And for the different values of C's, we have local powers between a little bit more than 5% up to 100%, depending on the C. So this is what you have with the other statistics. In general, rejection rates, again, are lower, with the positive effects in this case that you also have less oversize effects in this case, okay? Good. So maybe in the last part of my talk, I will show some pictures from a preliminary analysis that we started with for the empirical application in this paper, in which we are testing for latent factors in short subperiods of the CRISP data set. So we are going to consider the monthly stock returns in the CRISP in this periods, and we are going to consider short subperiods corresponding either to booms versus recessions in NBR classification, or we are going to use bear versus bull market classifications in the work of Alan and Lunden and Timmerman here. So here we have, just to have an idea, in the upper panel, the sort of pink or light red bars are the bear market phases. So these are the NBR recessions in this period, and this is the evolutions on the cross-section N. So that's the numbers of stocks that you have in the panel, stocks which have a complete history in the previous 12-month window. So this numbers grows from about a couple of thousands up to a maximum of 8,000. So that's to have an ideas of the cross sections which are used in this experiment. Okay, and so we have considered different subperiods. Here I'm showing the results from some of the subperiods that we have here. So this first one is a period with a bear market. And so in these two panels, I have on the left-hand side the eigenvalue spacings for the different J's. So these are the difference between the first and the second and the third and the fourth, etc. Eigenvalues. So some difference, the first one are quite large. Then you have, as we know in these kinds of plots, decay to very small differences. But of course, here, the whole story is to understand statistically whether these differences are significant or not. So that's the point, is to understand where these are statistically zero. And these are the ratios. Okay, so these are basically the inputs for the test statistics. So when you are using the first one, you are basically aggregating this differences here and testing whether they are large or not. And when you are using the ratio statistics, you are picking the largest of these ratios from k+1 up to a limit and see whether that's statistical significant or not. So for this period, these are the p-values that we get with the two statistics. So this one based on the largest eigenvalues. So these are the p-values when you test for 0, for 1, or for 2 factors. So for instance, when you test for 1 factor, you are rejecting at the 5%. You are not rejecting at the 1%, the hypothesis of 1 factor. You reject, sorry, you do not reject at 5% when you are testing, for instance, for 3 factors. That's the result with the other statistics, with the ratio. With this one, you do not reject the zero factor hypothesis. So this statistics is perhaps less powerful in this dimension. This is the result for another period. So that's a bull market period according to Lund and Timmerman classification. Again, on the left-hand side, the eigenvalue differences. On the right-hand side, these eigenvalue spacings ratios. These are the p-values. So in this case, maybe for k equal to 5, I think the p-values is slightly above the 5%. And these are the result with the additional statistics. So this is essentially what this methodology is allowing to do, so that you are essentially attaching a p-values for this test. So instead of having somehow a diagnostic criterion and selecting the numbers of factors about that, you are attaching p-values to this test. And I think, yes, we have another period, this one, that's a COVID period. So with a short t, you may do this kind of analysis. You take the 24-month that we classify, let's say, as a COVID period. Again, these are the eigenvalue differences, the spacings. So again, one very large, and then a few ones, but you don't know whether these are equal to 0 or not. And these are the ratios, and these are the p-values. So according to the statistics here, you do not reject the 3 at 1%, for instance, 3 factors, things like this. Okay, so so to conclude, so what we have done in this paper is essentially we have developed some new tests for the numbers of latent factors in short panels. So n is large, t is small, and essentially the challenge that you have here is to face with the incidental parameter problems that comes from the many betas that you have to estimate here. And so among the main ingredients for the analysis is in this short t framework is that on the one hand we exploit a sort of perturbation expansions on the small eigenvalues of symmetric matrices. So you can have a distributional theory to understand when the eigenvalues, an estimated eigenvalue that correspond to a 0 eigenvalue in the population matrix is statistically significant or not. And another ingredient is that because in some way or another, the asymptotic distributions are related to random matrices in some Gaussian families, more or less generals, we can draw results from this literature. And the setting that we have developed is somehow general enough to accommodate different forms of factors. So not only for testing against strong factors versus non-factors, but in this sort of continuum with different nuances of possible factors, including the semi-strong, the weak, and the vanishing factors. And for so far, for the empirical analysis that we are performing, so the p-values suggest that there is indeed, as we may expect, some variations in the numbers of factors across different market phases, with smaller numbers during bear markets or market downturns, larger numbers in market upturns. And in future versions of the paper, we will push forward this analysis, or there are many dimensions in which this has to be completed. So thank you very much.
Wonderful. Thank you, Patrick. So the first discussant is Markus Berger.
Thank you very much for the honor to discuss this great paper. So first of all, I really like the paper. It studies a very important question, and that is, how many factors do we have in a short panel? This is a very challenging question because, number one, we want to consider short panels, so t will be small. Number two, we also want to deal with weak factors. And now what this paper does, it will provide hypothesis tests for what the right number of factors should be. And as I pointed out, it's an important problem because essentially any paper that we have in the factor space always needs to start with determining how many factors do we have, and then we can study what are the properties of the factors moving forward. Dealing with small t is important because it allows us in a very simple way to deal with time variation and unbalanced panels. And dealing with weak factors is important because we know empirically, we usually don't have only a relatively small gap between some of the larger and some of the more idiosyncratic looking eigenvalues. So empirically, it seems to be more relevant to also be able to include weak factors. Now, this is a methodological paper, and it proposed a novel test statistic for testing what is the right number of factors. And what it does, it shows this asymptotic distribution for strong and weak factors. And it allows also for tests of weak versus strong or semi-strong factors. That is all based on a novel second order expansion. I also want to highlight there are a lot of ideas in the paper. So Patrick highlighted some of them, but there's a lot going on, and I highly recommend everyone to read this paper. I'm trying to summarize what is in there on one slide. So we study a standard linear factor model. That means we have a panel, we have t time periods, we have a cross-section of n assets. We assume a linear factor structure. And the conventional approach in the literature is when we have a large n and large t is to apply PCA. Then the number of factors is related to the eigenvalues of this principal component analysis. So large eigenvalues means we have a factor, small eigenvalues means it's idiosyncratic noise. And what estimators for the number of factors look for is a gap in this eigenvalue spectrum. And there's obviously a lot of work that is trying to detect how many factors do we have. But most of this work should be better described as a diagnostic criterion. That means this work uses some form of rate condition and can, based on this rate condition, say, well, the gap should have a certain rate, but there's always some proportionality constant for this gap. And that is essentially a tuning parameter. So determining the number of factors based on saying if a gap is small or large depends on a choice, a tuning parameter, which essentially means that the number of factors for a lot of these estimators becomes a tuning parameter itself. And that is where Patrick's work comes in, because Patrick will derive a distribution theory that allows us to test how many factors we have without this tuning parameter. So this setup will be large n and small t, and he will study two types of matrices. Either we look at a cross-sectional second moment matrix of our panel, that will be a t by t matrix, or we have access to instruments given for the main application. As stock returns, these instruments are firm characteristics. So essentially we form characteristic managed portfolios. Then we study the sample covariance matrix of these characteristic managed portfolios. Then we estimate the eigenvalues of these two types of matrices. And what they can show is a distribution result for the small eigenvalues. And that can be used to construct test statistics. So these test statistics will be based on eigenvalue differences, either the sum or the ratios of eigenvalue differences. And as I said, what makes it really important is it allows us to make a statement how many factors we have without including tuning parameters. Now, I have a couple of constructive comments that I think can help them to extend their paper moving forward. And the first couple of comments are about the assumptions. I mean, as everything in life, nothing comes for free. If you want to have these nice distribution results, it comes at the cost of assumption. And now I want to discuss how strong are these assumptions. So the first message that they have is based on this second moment, the covariance matrix. So they assume that this covariance matrix, it's not a covariance matrix, the second moment matrix based on the cross-sectional average, that this here is essentially the identity matrix up to some scaling. Now, under this assumption, the population eigenvalues of this residual second moment matrix would all be constant, the same, and that is the basis for the distribution theory. And the question is this a strong assumption? And that obviously depends on the application, but the key application here is about estimating the number of factors in stock returns. And assuming that stock returns or residuals of stock returns are not serially correlated, I think that is okay. However, there's a lot of time variation, the volatility, also of idiosyncratic stock returns. So I think the homoscedastic volatility assumption might not hold empirically. So what I think would be good for this paper is to show, at least in simulation, that there's some degree of robustness if we have a heteroscedastic matrix here. And of course, ideally, it would be nice to extend this theory to deal with a diagonal matrix that does not have the same value. Now, the second set of self-assumption is about the second method that we have in here. So this is the instrumented version. And as I said, intuitively, you should think about forming characteristic managed portfolios, and then you form a covariance matrix for a short time window, and then you study the eigenvalues of this object. And that is closely related to Fan's work about projected PCA. Now, the key assumption that is underlying this is that all factors can be identified from these characteristic managed portfolios. Now, there are two elements that I want to talk more about. So first, these characteristics or instruments are a choice. That essentially means the strength of the factors and the number of factors that we can find becomes a choice too. So it's possible that in individual stock returns, we have strong factors, but once we map them into characteristic managed portfolios, they become weak. Just to give you an example, if I have 100 characteristics, 99 are value characteristics, one is momentum. Of course, momentum will look weak in this panel that I've constructed. So the point here is it becomes a choice what a strong and weak factor is based on what instruments are selected. The second point is we need to ensure that we have all the characteristics that are necessary to find the factors. And we know there are a lot of candidate characteristics. I mean, it's easy to come up with more than 100 characteristics. And we also know that the world is unfortunately nonlinear. So when we do this, we are essentially dealing with a conditional factor model. And if we want to account for nonlinearities, we can do it to some degree if we use transformation of characteristics. Simple way would be to use kernels in the form of decile sorted portfolios. If I have 100 characteristics, I use decile portfolios, I end up with 1,000 instruments. My understanding is that the theory in this paper assumes that the number of instruments is finite and small. So it would be nice if this theory couldn't be extended to a large dimensional case. Now I want to talk more about the bigger picture here. So one is that the ratio statistics that are used here, it's all fine theoretically, but empirically, they might not be very stable. For example, empirically, you can observe that smaller eigenvalue ratios can explode. Now, I think one way to create more stability is to regularize these statistics by including a perturbation term that is of a very low asymptotic order. So that is not going to change the asymptotic distribution, but it can improve the finite sample performance of these type of statistics. Another more bigger picture point, I'm not saying you should change anything, but you could discuss it in your paper about what is a factor and what should be the right number. That also depends on what we want to use factors for. Now, this is about asset pricing in the end. How many factors do we have in stock returns? Now, if I want to know what the right asset pricing factors are, my goal is to construct a stochastic discount factor or SDF. So what I care about is a spanning criterion. And you know, there are a number of empirical papers that use Sharpe ratio maximization as a criterion to select the number of factors. That's quite different. I think spanning criterions have certain advantages. For example, they might be more robust or less sensitive to the selection of instruments. And that is an alternative way that can be discussed in this paper. Another point is about weak factors in finite samples. I mean, everything that we are doing will be based on finite samples. And in a finite sample, I don't think we can credibly distinguish between a weak factor that has a large proportionality constant and a strong factor that has a small proportionality constant. And just to give you an example here, that was what Patrick showed. That's one of his simulations. It's one of his test statistics where he shows rejection rates. And what I want to point out here is if you look at semi-strong factors with a small proportionality constant, they behave very similar to vanishing, so very weak factors with a large proportionality constant. So you cannot really distinguish these two. And so my view here is that all these rate conditions are only a tool. They're a tool to derive a theory that we can use to make decisions. And what matters in the end is that the decisions that we made with this theory work empirically in a finite sample. So I think some of this discussion about all knife edge cases of rates might be empirically not first order. Now, about the empirics, there's a very nice empirical application. So my understanding is that it includes all stocks. It means also penny stocks. And penny stocks get the same weight as some of the largest stocks in the sample. So it would be nice to see the results after excluding all the small penny stocks. My understanding is also that there's a lot of time variation in the composition of stocks and also the number of stocks that we have here. It might also be nice to see the results for a more homogeneous panel, for example, the S&P 500. Another thing that you might have seen before was that the number of factors that would come out of these statistics can be different depending on which statistic is used. And I think that it's partially due to that some of these statistics are sensitive to certain issues. For example, the maximum ratio is sensitive to a very strong dominating factor. It's also sensitive to vanishing idiosyncratic eigenvalues. An eigenvalue difference statistic is sensitive to what the smallest reference eigenvalue is. And it would be helpful to discuss more why the results are different with these different statistics. And I would also encourage you to think more about alternative, more robust test statistics. I mean, you have this really nice theory for the distribution of eigenvalues, and there are a lot of different statistics that you can construct. One would be the LR test statistic that Alexei will talk about. You could include these perturbation terms that are not changing distribution. It would be nice to see if that gives you more robust statistics. Finally, I just want to talk about the very big picture. So one important part of this paper is about weak factors and making statements about those. So what is a weak factor? A weak factor is a factor that has a small signal based on its covariance matrix. And I think this paper here is complementary and also very supportive for a bigger literature on these weak factors, because a factor is weak always depending on which signal we use. So you can make factors that are weak in the covariance matrix stronger by using more information. One example would be to include other moments that can push up the eigenvalues. You could use the correlation with other target times here, that would be scaled PCA or Stefano supervised PCA. So I have some work where we use multiple panel data sets, and you use the relevant information from another panel that is useful to explain a target panel. We have another paper where we use economic restrictions, which will also have an effect on the signal in your target panel. And all of these papers have ideas of how to transform data such that factors become stronger. So essentially, all of these papers apply principal component analysis to transform data. And because there's some transformation, eigenvalues will get larger. But all of these papers also need to take a stand on how many factors are in there. And I think there is an opportunity for you to apply your theory to these transform data matrices. First of all, to say how many factors are there, but even more importantly, all these papers have tuning parameters in one form or the other. And the tuning parameters are chosen to make a weak factor stronger. But now you have a theory about the distribution of factors, and that can provide guidance of how to select tuning parameters in these papers. So let me wrap up here. So this paper studies a very fundamental and important problem. It proposes a novel test statistic based on a new uniform perturbation result. It is very nice that it can deal with factors of different strengths. And it's also very nice that it contributes to this highly relevant problem of weak factors. And so overall, my conclusion is, please read this paper. It's a very interesting paper. And thanks for the opportunity to discuss it.
Thank you, Marcus. So the next discussant is Alexei Onansky.
Well, first, I'd like to congratulate authors on great paper. And I agree with Marcus that there is a lot of things in the paper, so I will not be able to discuss all of them. I will discuss a very small fraction. So in particular, I will focus only on the proposed tests based on the eigenvalues of the simple covariance matrix, and I will not be talking at all about anything related to instrumental variables. And I think that part of the paper is also very, very interesting. So I just don't have enough time to discuss that. Okay, so what I will be talking about, I will have two main comments and a couple of secondary comments. The main comments will be about the possible misspecification or possible identification problem. So this assumption of proportionality to the identity matrix. And then I will propose to use maybe, instead of principal component analysis, the classical factor analysis to potentially fix this. And in the additional comments, I will speculate on, well, maybe you can use certain technique to test for potential identification problem, and well, it seems that this may work. And finally, well, I like this computational methods introduced and discussed in statistics literature recently, such as parallel analysis. And I thought, oh, maybe parallel analysis will work here, but turns out that it does not. And I will talk a little bit about that. Okay, so potential identification problem. So that is the model considered. So you have some data, I indices cross-section. This is a t-dimensional vector because there is t time periods, and there is factor loading, and error. And then there is this important assumption which is used to develop this test. The assumption is considering this kind of sample covariance type matrix as n goes to infinity, and says that this is proportional to the identity matrix. And this assumption would be no assumption in macroeconomics, right? In macro data, this would be no. So, but in finance, if you're working with stock returns data, I thought that well, maybe this is not that bad assumption. Epsilons are martingale different sequences. Well, maybe the Garch something, and you have independence cross-section also. Of course, when you cross-sectionally average this thing, well, maybe this will converge to unconditional variance covariance over time. So this should be proportional to identity. Okay, and then I thought that, well, in fact, well, some recent literature points out on the existence of a pretty strong factor, not in idiosyncratic terms themselves, right? So there is no factor in idiosyncratic terms, but in the idiosyncratic volatility, right? The factor in idiosyncratic volatility. So the volatility for all these epsilons is changing very similarly across a lot of stocks. So what this would mean that this V epsilon cannot wash away the conditional variance of a common factor in the idiosyncratic volatility. And potentially this will lead basically not to the proportionality to identity, but to proportionality to some diagonal matrix, but not necessarily identity. Now, will this diagonal matrix be big? Well, maybe it will be close to identity. Maybe it will be just slightly changing the terms along the diagonal. But remember, we here are talking about testing not only for strong factors, but also for weak factors and this kind of stuff. So even small deviations from the identity here would be super important, right? And I kind of have feeling that that this may be violated because of this strong factor in idiosyncratic volatility. And just to illustrate, and I'm kind of exaggerating here the strong factor in volatility, but just to illustrate the effect on this test, first of the two based on the difference of eigenvalues. So I considered Monte Carlo experiment the same design as in the paper, but I changed it a little bit. Instead of this variance just to be independent of t, I also included just multiplied by t. So it's diagonal matrix here, but proportional to time. And then the actual size of the test completely explodes. It becomes 1. So so this is not good. And then I thought that what can be done? Well, and here actually you can think about this model really as the classical factor model, except that factors here are playing the role of loadings, and loadings are playing role of factors. So usually in classical factor analysis, so there will be, well, a lot of observations, n, right? And this will be factors. And this will be vector of loadings, fixed dimensional vector of loadings. And then you will be assuming that that this guy is diagonal. not necessarily proportional to the identity matrix. And of course, you will assume that this thing is random factor. Well, so then, well, there is a well-developed theory for how to estimate things in this classical factor models. So usually this theory is developed under normality, but there is a lot of results under non-Gaussianity. So in particular, you can use the standard likelihood ratio test of null hypothesis for k factors, and this will be based on this likelihood ratio statistic. It's basically minus n, and then sum of j going from k plus 1, where k is the number of factors under the hypothesis, up to t, log 1 plus gamma hat. What is gamma hat? Gamma hat is the, well, like 1 plus gamma hat is the eigenvalue of this matrix. What is that? That is the familiar matrix used by Patrick. But then you multiply it by inverse of the diagonal matrix, the estimate of that thing, maximal likelihood estimate of that thing. And well, under normality and homoscedasticity, which is, by the way, not the assumption in this paper. So here, like in this paper, things are heteroscedastic. But suppose that there is homoscedasticity, normality, then this thing is distributed as chi squared with certain, well, degrees of freedom. Now, and you can just use it. So now I don't want to use normality and homoscedasticity. So the well, goal then will be to derive asymptotics of this likelihood ratio statistic under non-normality and heteroscedasticity. And actually that probably can be done, because the asymptotic of that thing essentially will depend not on the normality or like homoscedasticity, but it completely will depend on the asymptotic of that matrix. Because asymptotic of this matrix can be derived from the asymptotic of that matrix using the results in Anderson and Rubin in 1956. So there will be kind of joint asymptotic analysis of that thing, and that thing just based on how this behaves. And you don't need to make assumptions of normality or homoscedasticity to figure out how this behaves. This is just very relatively simple object, this sample covariance matrix. And you can derive properties of that and then of this and then combine. So, well, my hypothesis that this can be done. Now, so now this were essential comments, now become kind of secondary comments. Well, perhaps you even can test for this potential identification failure, because there is another likelihood ratio statistic which is based on the assumption of this proportionality to identity. So the previous one that I showed is just assumes diagonality, but suppose that your assumptions of proportionality to identity hold. Well, then likelihood ratio statistic will be more complicated than this delta 1 minus delta like something. It will be like this. And it's known result by Anderson in 1963. And this under homoscedasticity and normality is distributed as chi squared with that different degrees of freedom. And well, so now you can take the difference of this statistic and the statistic on the previous slide, and the difference between this degrees of freedom and the degrees of freedom on the previous slides. And so this will be a test statistic for testing this additional assumption of proportionality to identity. Under normality of homoscedasticity, it will be distributed as chi squared with t minus 1 degrees of freedom. Very, very simple. And well, so you can, if it is larger, you should probably use factor analysis, classical factor analysis instead of principal components analysis. If it is smaller, go ahead with principal components analysis. Of course, the challenge would be to generalize to non-normal heteroscedastic situation. I wanted to put scared emoji here, but I couldn't. So why is that? Well, because, you know, in addition, you will need to know the joint distribution of that and this, in addition to previous slide. And even Anderson in his book is saying, well, you know, what the asymptotic distribution becomes a bit complicated here, so I will not report it. So I thought, okay, but it exists and it derived in that Anderson and Rubin paper. And by the way, as Marcus said, so you can use this likelihood ratio statistic as the alternative to a couple of your other statistics. And well, potential advantage of this will be that, yeah, it's a pseudo likelihood ratio statistic, but it's still like under Gaussianity, because it is likelihood ratio statistic, maybe many things will cancel out, and at the end it will have nice distribution. And yeah, under normality, instead of all this Gaussian orthogonal ensembles and like all this random matrix theory, you just have familiar high square distribution, like for example, for the distribution of this likelihood ratio statistic under the alternative and under your assumptions. Okay, so okay, now my last slide would be about this parallel analysis. So let me tell you what parallel analysis is. Parallel analysis is a very, very popular technique and was attracting a lot of attention recently in more theoretical statistics literature. For example, there is an Annals of Statistics paper by Edgar Dobribon. Well, parallel analysis is based on this permutation techniques. You just destroy factor in your data by randomly permuting data matrix row by row. So you just take first row permuted, take second row permuted, and take, well, et cetera, et cetera. So you get completely destroyed factor, and then you look at eigenvalues or singular values of this matrix and compare with the singular values of the original. And you start then from the first singular value of original and compare with the singular value of destroyed. And if it is bigger, or like, well, then you say, okay, there is one factor. Then go to the second. If that second is bigger than the second eigenvalue or singular value of destroyed, there is second factor, et cetera, et cetera. And I thought, oh, maybe here it will work. And I tried using the Monte Carlo analysis proposed in the paper. And this method actually often underestimates the number of factors here. And I thought a little bit about why this might be. And then I thought that it's very natural here, because so what happens when you destroy factor? When you destroy factor, you kind of transfer variance, which was systematic, from the factor to idiosyncratic part. And this will result in the kind of inflation of the smallest eigenvalues. So this technique is always very conservative with respect to like just estimating more and more factors. It doesn't want to do that because it kind of inflates smallest eigenvalues. And so it doesn't allow you to estimate more than needed factors. So no, you cannot do this popular parallel analysis. You should probably do what you're doing. And my suggestion, maybe look at this classical factor analysis if possible. That would be wonderful. Thank you very much.
You want to give a short reply, Patrick?
Maybe just a couple of things which are common in the discussion. So one very important concerns this assumption ones. It is less restrictive. It is restrictive, less restrictive than what it may mean. So it's important to realize, indeed, as Alexei was pointing out, that it allows at the individual level the conditional electroscedasticity. What is really excluding is indeed some common factors, common strong factors in the idiosyncratic volatility. So then this becomes indeed perhaps an empirical question how this is important or not. So we were indeed considering to investigate the sensitivity of the statistic to this, maybe in Monte Carlo or in theory. We were also thinking about whether some transformation indeed of the data may help us in bringing this the data closer to this condition. Another way to test would be maybe to contrast with the other approaches for identification, which is by means of the IV approach, which is not using that. That could be another way to test whether this assumption is altering the data. Also, maybe the small t dimension helps in controlling for that. So it's it's going to be easier to maintain this assumption over short t than rather than big T. We might test maybe splitting the time dimension in two. So we are considering some of these issues. Then maybe factor analysis. This is a brilliant suggestion. Thank you so much, Alexei. So this idea of switching the INT is very clever. I think that maybe one issue that it would be perhaps challenging, I don't know, is how do you think in this case to the incidental parameter problem, in the sense that in classical factor analysis, in the simplest way, you assume that not only the error, but the factors are Gaussian distributed as well. So now when you switch, your factors becomes the beta. So I think that in principle, the full analogy would be something like a random effects in our case. So something like assuming that the betas are random. So what is doing here with PCA is indeed something like fixed effects. So maybe the analogy is possible. I think it's some work to be done, not only in the extensions of the Gaussianity of the errors, but I don't know how it works with the random versus fixed effects. So to me, it would look similar as using some random effects or Gaussian priors to address incidental parameters in panel problems. So it's definitely worth while exploring. And I like very much the suggestion of the likelihood ratio. This is very, very to the point. So we could in principle very easily. Indeed, what I like is that if you look at the slide of, if I may use, oh no, in one of the slides of Alexei was showing, you see that the likelihood ratio statistics, oh yes, is indeed the log of the average eigenvalues minus the average of the log eigenvalues. So it's a sort of Jensen gap. And so the idea is that indeed, if the assumption is correct, that the eigenvalues becomes constant, instead of using that the eigenvalues differences are zero, you are using something like the fact that there is a gap between the average of the log and the log of the average. So that could be a different approach, and with the theory that we have in the paper, in principle, we can extend directly to the Gaussian or non-Gaussian, and that would be another way to aggregate the eigenvalues, maybe in a more clever way. So that's definitely a very good suggestion. Thanks a lot, and I think I will stop here.
Thank you, Patrick. I guess we have maybe time for one or two questions from the audience. Well, if there is no one, I have to do one. Ah, yeah. Alan.
Yeah, thanks very much for a great talk. One thing I was thinking about is, so imagine as you find empirical indeed that the number of factors varies quite a bit, say between bear and bull markets, so 1 to 3 in the bear markets, 5 to 7 in bull markets, and then you come along and you estimate, you know, somebody doesn't account for that and just estimates the number of factors on the full sample. Can you establish results on what would happen? And I guess you would need to make some assumptions about the proportion of the full sample spent in the two states. But of course, then again, if you have, you know, like generating breaks where you don't have you know, the same states repeating, I mean, can you characterize what will happen? Is it like, you know, the maximum number of states you're going to pick up, or what's likely to happen?
Yeah, this is very nice and very challenging question that we were considering that. Maybe we're considering whether in some toy examples we will be able to find that. I think that in principle it can go in both ways. So like so if some of the factors disappear are in some periods only, then you may think that you might find a lot of factors in some periods, but very few of the full sample, because maybe some of them are there only in short periods that disappears in the entire. That could go in one dimension. In the other dimension, you can think that is something like, you know, it's like if you have imagined that there is some variation in your betas in fact. So what you see is a variation of the beta. So unconditionally, you would see more factors than conditionally. So I think that in principle, the solution is open to having more or less factors conditionally versus unconditionally. And so we take your suggestion. So we would like to see whether it's possible to figure out some examples, maybe simple models in which it's possible to make a statement about what you're finding, whether maybe, well, I can imagine that in some situations, what you find unconditionally is halfway between what you have in this. And also what you don't know is to some extent whether they are the same factors. So what could be possible and has been done in other work is that you somehow look at the canonical correlations between the betas estimated in the two subpanels to see to which extent indeed the factor structures overlap between the two.
And maybe I have a related question to the point of Alan. So in the simulation, it looks like that the size of the test was not so sensitive to the choice of t, while the power is. So in a way, if you start to get into a setting where you have in mind some time varying factor structures, it looks like the choice of the length of the period is what is going to be key to find the factors even when they're there. So did you try to, for example, have a kind of data-driven approach by which on rolling windows, you start to look at how many factors are there and how they change, and look at as a function of the length of the t parameter, how the type of results are going to change?
Yes, thanks, Fabio. That would be a possibility. So the rolling window approach, it has advantages and disadvantages. Maybe one disadvantage is that if there is really something like, so imagine that there is really a neat change in the numbers of structure. Maybe that's not the case, but imagine that there is really a neat change in the numbers of structures depending on the market phase or some conditionings. If you do rolling windows, you probably mixed up a little bit. So this is what we were seeing in very, very preliminary results. So we were happier to show the pictures with some exogenous classifications, because at least it seems to us that we got more interpretable results. Having said this, perhaps also exploring further with other statistics that might be.
But basically, the simulation, they indicate that you really need to have a change in factor structure, which is sufficiently there for sufficient time in order to be able to find it.
To have power.
Yeah.
So the power grows with t, of course.
Yeah.
Yeah, that's true.
Okay, great. I think it was a fantastic session.